Lectures in Physics for 2013, celebrating the discovery of the quantum atom 100 years ago. My name's David Jamieson. I'm the head of the School of Physics here at the University of Melbourne and the organiser of the July Lecture program. It's an enormous pleasure to invite Associate Professor Harry Quiney to give his inaugural July Lecture in Physics tonight. Harry has a distinguished track record in research across the Commonwealth. He obtained his Masters in 1984 from Monash University and then went on to do a DPhil from the University of Oxford in the physical sciences. He's been a senior scholar in some of the well-known Oxford colleges and held a distinguished fellowship in doing so. He had already established a distinguished career in research in Oxford in the field of theoretical atomic and molecular physics, applying the Bohr theory, I should say, as it is in the 20th and now the 21st century, before he returned to Melbourne and joined us in 1998. He took up a position as a program leader in the Theory and Modelling program in the Australian Research Council Centre of Excellence for Coherent X-ray Science, and is also an Associate Director of the Centre. And I'd like to issue a special welcome to Professor Leanne Tilley, who's present tonight, who is the Director of that Centre of Excellence. Recently, his research at the frontiers of atomic and molecular physics has moved into applications in the imaging of biological materials and structures, and he's pioneered techniques involving the reconstruction of images coming from state-of-the-art free electron laser systems, and has been well recognised for this. In 2011, he won the David Syme Prize for Research, demonstrating the very high level of his work. In addition to his research program and the teaching he conducts in the school, he also conducts the Growing Tall Poppies program through the Centre for Coherent X-ray Science, which has introduced many school kids to the wonders of research with X-rays at the frontiers. So it's a great pleasure to invite Harry to give tonight's July Lecture.
Thank you, David, very much for that very generous introduction. It is indeed my inaugural July Lecture. It's a great honour and a privilege to be here this evening. This evening I'm going to talk about Moseley's law and the progression of X-ray physics from the days of the Bohr atom in 1913 to current research which is being conducted here in the University of Melbourne and across a network in Australia, which is the Centre for Coherent X-ray Science, we'll leave you with a few thoughts about the relevance of this work in this centenary celebration of the Bohr trilogy. So the overview of the talk is I'll talk about Henry Moseley and Rutherford and Darwin and Bohr and the publication of Moseley's high-frequency spectra of the elements, which occurred at the end of 1913, 100 years ago this year. I'll go on to talk about the consequences of that to the theory of atomic structure and inner shell spectroscopy, and then I'll go on and tell you a little about what we're doing now in CXS and with our collaborators across the world, investigating the use of new X-ray sources to determine the structures of matter, and a third revolution that's taking place in scientific research. Now, 1 year ago, as David reminded me, 1 year ago was the ICHEP conference, International Conference on High Energy Physics, which was held in the exhibition centre here, and all the world's leading particle physics gathered together in that conference, and through the miracle of modern technology, the discovery of the Higgs boson was made at the conference. Live from CERN, finally confirming the Standard Model, and the School of Physics at the University of Melbourne was at the heart of events, and many of you will remember discussions of this last year. But this is certainly not the first time that the School of Physics at the University of Melbourne has been at the centre of the action. I take as my theme for quite a bit of today's talk a meeting which took place 99 years ago, the British Association for the Advancement of Science, obviously the Australian government thought that science was important in those days. It invested £15,000 to host this meeting in Australia, which was a sort of travelling circus between Adelaide. It then moved to Melbourne and then to Sydney, and ultimately parts of it went to New Zealand. Now we're in a very happy position that there's a 1,000-page record of this meeting that one can download and go through, and it's a snapshot of Australian science in 1914. It's not just science and the kind of science that we do in the university. It's also a snapshot of science participation, because the back half of this document lists all of the Australian members of the British Association for the Advancement of Science, and it's not just professors and leaders of science, it's school children and school teachers and members of the PMG and members of companies. Many people merely gave their addresses university. Some people gave their addresses Methodist Ladies College. It covered a vast spectrum of the population of these major cities. Now, this delegation was led by Sir Ernest Rutherford, and the cutting-edge science, cutting-edge physics of 1914 in that period was atomic physics. The structure of the atom, the consequences of Rutherford's model of the atom, Bohr theory, and Moseley's X-ray survey of the elements. And while one can't dispute that the discovery of the Higgs boson was a monumental event, it was an event that was sought for 50 years, more or less, from 1964 until last year. If you read this document, it tells you the state of confusion of science in 1914, and that the concepts that we regard as commonplace and everyday now were matters of serious and heated debate 100 years ago. And 99 years ago, and about 150 yards away, was this joint meeting between Section A, which was the physical section of the British Association, and Section B, which was chemistry. Chairing this meeting was Sir Ernest Rutherford, and Sir Ernest said, well, I think we can all agree about my model of the nucleus, and Thomson's made some quite good contributions to science over the years, the electron and so forth. But clearly the models that we have of atomic structure are really kind of not explaining how things are going. He goes on to say that there is seen some great insights by Mr. H.G.J. Moseley, M.A., about whom much more in a minute. And he made the following observation, which is as true today as it was 100 years ago. We have now two powerful methods that aid us in determining the inner structure of the atom, the scattering of high-speed particles in transit through matter, and the vibrations of the interior parts of the atom. And in modern lingo, that's scattering and spectroscopy. Scattering, the structure of matter included Bragg X-ray scattering, which had been demonstrated a couple of years before from periodic solids. And spectroscopy, he was speaking in particular of the very recent work of Mr. H.G.J. Moseley, M.A., who was working with him in Manchester. This is true today as it was in 1914, and it would be very unfair of me to pick through the transactions of this meeting and point out all of the things which today seem ludicrous, but some of the things are as true today as they were then, enduring observations and insights into matter, and Ernest Rutherford was certainly successful in that. Now, David quoted this last week, but it's so good that it has to be quoted again. After Sir Ernest finished his address to the meeting, Professor Armstrong, who was a young chap, he was Professor of Chemistry at City and Guilds College in London, stood up and said, the arguments presented by Sir Ernest are so novel, so daring, and contentious and so original that at present they, by which he meant we chemists, are not in a position to appreciate them, less still to criticise them effectively. He went on to say that physicists, unfortunately, in the past have held aloof from chemists that they were living in different worlds, that they were concerned about different things, and he did rather dismiss the discussions by Rutherford and Moseley about the structure of the atom as being irrelevant to chemists, because everyone knew that chemistry is really about periodic behavior, chemical reactivity, and valency, and the Bohr theory really had nothing in it for him. And unfortunately, he was wrong, because Bohr theory really was the key that led on to so much, and ultimately led to most of all of the physical theories of structures and particles that we have today. But nevertheless, he welcomed the physicists and said that perhaps there would be some value in the meeting. So part one of the talk is we'll discuss the roles played by Ernest Rutherford, Henry Moseley, and Niels Bohr. Now, Sir Ernest, of course, was famous mainly for theories of and experiments on radioactivity. Moseley and Bohr were approximate contemporaries and of a similar age, and both found themselves through a series of events that started in Oxford and Cambridge, ended up in Manchester. Now, as a small revision of what's gone in the previous two July lectures, we'll remind ourselves that the Planck relation relates energy with frequency through the Planck constant, and that, as David demonstrated last week, the Rutherford atom posited a highly concentrated positive charge within a tiny volume on the orders of femtometers. The Bohr electron theory was a model that suggested electronic orbits around the nuclei on length scales of angstroms, which is 10 to the minus 10 of a meter, so there's 5 orders of magnitude between the radius of that and the radius of that. Bohr suggested the quantization of angular momentum in multiples of h bar, and the additional postulate of quantum jumps, discrete jumps between these quantum energy levels, whose energies and frequencies and wavelengths were related to the Rydberg constant. And the Bohr formula, in a form that's convenient for later use, is that this energy, h nu, is equal to this set of constants. It scales as z squared, where z is the nuclear charge, and depends on the difference of these quantum numbers n1 and n2, which label the orbits of the jumps. And the triumph of Bohr theory really is that he determined R from a theoretical model such that this Rydberg constant depended only on fundamental quantities like the mass of the electron, the charge of the electron, the vacuum permittivity, Planck's constant, and the speed of light. The eagle eye amongst you can see that the speed of light cancels out trivially here, but that's only because I wanted to work with frequency rather than wavelength. Which brings us to the star of the show, which is Henry Gwynne Jeffreys Moseley. Henry Moseley was known as Harry to his friends, which has always endeared him to me. I went through my entire undergraduate career as a chemist, never really hearing the name, and preparing this lecture, I went through a collection of undergraduate textbooks in physical chemistry, and he seems largely to have been excised from memory, and I think that's a great shame, because, as I think we'll see in a moment, he made a fundamental contribution to understanding the periodic structure of the elements, and to understanding the nature of chemistry. This is a picture, it's a most evocative and in some ways heartbreaking picture if you know what's coming up next. Here is Moseley in 1913. He's holding an X-ray tube, rather like the X-ray tube that we've pulled out of the Physics Museum here. You can see that this bulb is identical to this one. I don't know what this dates from, but I think it's the 1950s. The design hardly changed really. It basically consists of a metal target and a stream of electrons. When the electrons hit the target, they produce X-rays. Moseley is in the Trinity Balliol Chemistry Laboratory, which I've personally been in many times. These days it's called the Dyson Perrins Laboratory in South Parks Road. And in the original print of this, it's a very large format gelatin print you can read the labels on all of these bottles, and one of them is erbium. This was the chemistry lab in which Moseley was almost certainly sampling the elements that he used in his studies of the periodic table. This is Moseley, aged about 26. It's a snapshot of everything about him. Here's his X-ray tube. Here is an angle measuring device for measuring the diffraction of the X-rays that are produced. The room is lit by gas lamp. My grandmother still had the gas lamps intact in our house in Elsternwick when I was a kid. Didn't work, but they still had all this structure. And it has this, it's actually a flaw in the film, but it looks like a ray of light coming in. Actually, it's just a trick of the light. Now, Moseley himself, I think it's also important to know who Moseley was. Moseley's father and both of his grandfathers were fellows of the Royal Society. He came from an academic family. His father was a mathematician. His grandfathers were physicists and a conchologists, which is a study of seashells. And his mother was British amateur ladies chess champion in 1910. He went to a rather intense academic prep school in Oxford called Summerfields. He won a scholarship to go to Eton. He won another scholarship to go to Trinity College, Oxford. And he studied mathematics and physics. He got a first in mathematics and, paradoxically, a second in physics. This perplexed everyone because, by universal acclaim, Moseley was the most brilliant, the most lively, the most talented physicist of his generation. So, Rutherford knew that. Rutherford had a bit of an eye for talent, and he knew that Moseley hadn't really performed to the level that was expected. And so he said, well, why don't you come and work for me, with me, in Manchester? And so he recruited Moseley to go and work in Manchester. Moseley started off his experimental career in radioactivity and the properties of radioactive elements. But in a phenomenon that I'm becoming quite familiar with my own students, Moseley and Darwin, who was contemporary, and the grandson of Charles Darwin, of the Origin of Species fame, they got together and they'd seen Bragg give a talk, and they thought, you know, we should actually start looking at X-rays. And so they went to the great man and asked Rutherford whether they could do research in X-rays, and the identity of X-rays as particles had never really been established to look into. And Rutherford said, no, we don't do that kind of thing here. I prefer that you carried on doing radioactivity studies. But they persisted. Moseley was then sent to Leeds to meet with Bragg, and Bragg shared the technology for producing X-rays and designing X-ray sources. Moseley and Darwin got together. It was apparently Moseley's insight that led to the design of an X-ray spectrometer that allowed him to separate the wavelengths of the light that were produced. And this was published in exactly the same volume of Philosophical Magazine that the first of the Bohr trilogy was published. Now, a little reminder for some of you, and perhaps the first time for others, is that Bragg's discovery about X-rays is if you shine X-rays onto a crystal, the planes of the crystal reflect the X-rays, so that the X-rays come in here, they bounce off the crystal planes and eject it out this way. And in doing so, they undergo an optical path length difference. If the optical path length difference is equal to a multiple of the wavelength, then you get constructive interference in this direction. And all of this is encapsulated in Bragg's diffraction law, that if I have a multiple of the wavelength, I will observe a maximum of intensity at an angle theta if the spacing between these planes is d. And it cuts both ways. If you know d, you can work out lambda, and if you know lambda, you can work out d. It's an interesting question if you don't know either. Actually, Moseley and Darwin pondered this for a while, and they came up with an ingenious way of estimating the likely spacing in these planes. based on gravimetric measurements of the mass of crystals, and they tried this out for different crystals and different wavelengths, and finally came up with a calibration table between lambda and sigma, lambda and theta, for particular targets, and that allowed them to calibrate all the experiments. And so this is it's actually the Moseley Darwin spectrometer. You have a source of X-rays coming in here, a crystal being used to reflect the X-rays off the planes, and an X-ray detector, which in their day was a Geiger counter. And as luck would have it, we actually have one here. I always get a bit nervous when this happens, so we'll go to other sources, go to auxiliary inputs, push that one, and push that one. This camera here is actually centered on the X-ray device. It actually has an X-ray source, which is here, and the crystal is actually that object there, and then the detector is out in this direction. So, which one do I flick?
Power.
Power. I should explain I'm a theoretical physicist. Okay, so what Steve's doing now is he's actually transiting the angle through one of those critical points where n lambda is equal to 2d sine theta. And you can see the very big deflection on the current meter over there. That's actually telling you that there's a large number of X-rays going to the Geiger counter, the Geiger counter is being ionized, causing a current flow, and if you move the angle just by a tiny amount, the current produced is negligibly small, which is telling you that you have destructive interference everywhere, except for a couple of special values of the angle. I think we're coming up to the next one. There we go. So we've got our salt crystal at sodium chloride, and the sodium chloride crystal is diffracting the light and producing Bragg spots at the critical values of the angle that satisfy the Bragg diffraction formula. Well, Moseley, thanks very much, Moseley and Darwin actually produced a device rather similar to this. It was an X-ray source rather like the bulb source you can see over there, and a diffractometer which was various crystals that they sourced, and the detector was indeed a Geiger counter, and they measured the angles between the diffracted light, which allowed them to measure the critical peaks. Now, here is actually quite a good picture of a typical X-ray tube. This is the target that's hit. There's a beam of electrons coming here, hits the target at very high energy. It causes an excitation of the atoms in the metal and produces X-rays in this direction, which are put through a collimator and then effectively used as a source onto a crystal, which is then diffracted to a detector. And the design of these tubes hardly changed since Moseley's day, since Moseley actually designed most of them. Here's an actual, so, thanks. So, previous source was computer, that one. Do not. So this is a picture of Moseley's actual X-ray tube. It's in the Oxford Museum of Science. It's been preserved along with the spectrometer and a lot of his equipment. Moseley produced these X-rays by bombarding metal targets in vacuum with high-energy electrons, and he was able to build his own equipment. Moseley's great achievement, really, was that he was handy as a glass blower, and he was handy at making things. And that allowed him to work industriously and on his own. It's said that Moseley worked until about 3 in the morning. He rose at about 9 in the morning, and he lived almost exclusively on a diet of fruit salad, cheese sandwiches, and whatever he could find in Oxford or Manchester at 3 o'clock in the morning. Having lived in Oxford, it was the Carfax chippy on high street. Now, Bohr and Moseley were also contemporaries, and both went to work for Rutherford in Manchester. As I think David's probably told you last time, Bohr was originally in Cambridge and had proud parents who bragged that their son was in Cambridge, but he didn't like it that much. He found that no one would listen to him, and he couldn't really engage anyone in discussing his theories, and they said, oh, well, I'd have to see it all written down, wait until the book comes out. But by chance he went to go and see Rutherford in Manchester and struck up a relationship with him, and Rutherford offered him a position, and Bohr and Moseley were there at the same time. So Moseley was extremely well acquainted with Bohr's work and the Bohr atom, to the extent that this is a copy of a reprint of a paper by N. Bohr, D. Phil Copenhagen on the theory of the decreasing velocity of moving electrified particles passing through matter, and the inscription at the top says, Mr. H.G. Moseley, with the best compliments of the author. So this was given by Bohr to Moseley as a gift in 1913, and was sold at auction last week for about £25,000. Now this is Moseley's law. Moseley's law says Moseley conducted all of these experiments, and I should really go back to the previous slide. He wrote to Bohr in Oxford. He left Manchester to be with his ailing mother in Oxford. He decided to work on his own with no salary and with no position, and he carried out his experiments on his own. On the 16th of November 1913, he wrote to Bohr, and he described his results as extremely simple and largely what you, Bohr, would expect. Well, I can't see how Bohr would have expected anything, really. But what he really meant was that the energies or the wavelengths and frequencies of the light that he measured by X-ray scattering coincided with the same pattern of energy levels of Bohr theory. And even though there was not yet a manuscript, it actually mentions in the letter, I haven't written any of this up yet, and I'd like to point out it's the 16th of November. He also said in the letter that the results would appear in the December issue of Philosophical Magazine. And they did. And Rutherford saw to it. It turns out that Rutherford Philosophical Magazine were waiting for the next contributions from Rutherford's lab, and Rutherford put forward this paper in front of his own, actually, to make sure that it was published in the quickest possible time, and so it was published on December 14th, 1913, 100 years ago this year. So this is Moseley's law. That the frequency of the X-rays emitted in one of these quantum jumps is 3/4 of fundamental constant multiplied by z minus 1 squared, where this is the frequency of the emitted X-rays, which he was able to measure with a device rather like the one we've just seen. R is the Rydberg constant, Z is the atomic number, which has to be an integer, and C is the speed of light. And that this appeared in Moseley's high-frequency spectrum of the elements number 1 in 1913. And it was followed closely thereafter by the second part of his work, which was a comprehensive study of the elements. He scoured Oxford for chemically pure samples of all the elements and put them in his device, which he'd made it interchangeable, so it was very easy for him to change the target material in his X-ray tube. And he plotted the square root of the frequency against the atomic number and found that they fell into straight lines. By doing so, he essentially clarified and, in my mind, revolutionized the concept of chemistry. Because up until that point, this positive charge that was assumed to exist inside the atom, no one knew that it was an integer. No one knew it was an integer of the electron charge. There are all sorts of wild and wacky theories out there about chemical structure. There were kind of continuum models. A lot of people still believe that each element was unique and that they weren't constructed from the same building blocks. Moseley's law really put paid to that. This demonstrates that this positive charge goes up in increments, and up until that point, the atomic number merely represented the position on the periodic table, and the means by which elements were arrayed on the periodic table was atomic weight. Atomic weight was seen as being the fundamental quantity. So Moseley's survey of the elements achieved many amazing things. This hypothesis about the integer nuclear charge was known as Van der Broek's hypothesis, that it was an integer and that it was an integer multiple of the electron charge, that the periodic table of the elements is organized by that number and not by atomic weight, and that the X-ray lines provide direct evidence for Bohr theory because they correspond, or they're actually proportional to the square of the nuclear charge, and that factor of 3/4, as we'll see in a moment, had a significance in terms of the jumps. He managed to resolve the correct positions of the elements cobalt and nickel, elements 27 and 28. He predicted the existence of elements. There were gaps in the periodic table at 43, 61, 72, and 75, and these elements were discovered subsequently to Moseley's survey of the elements. All of them are either very rare or radioactive, so they're decayed very quickly. He resolved a long-standing chemical problem about the number of lanthanides, which range between 15, which is the correct number between lanthanum and lutetium, up to about 35, simply because the lanthanide elements come in many isotopes, and they have many atomic weights, and they have many valencies, and their correct order is very difficult to distinguish on the basis of chemistry alone. And he also identified the concept of, or verified the concept of the isotope. So he was able to verify that radium B was actually an isotope of lead, because it had the same chemical properties but vastly different weights, and so he established the reality of the concept of the isotope. And those lines, those almost but not quite parallel lines that were plotted out on the Moseley plot, are actually relativistic effects which are due to fine structure. So those two papers contained all of this information. They resolved the periodic structure of the elements, they pointed to the existence of relativistic effects, they verified the Bohr theory of the atom, or certainly gave great weight to it, and also resolved long-standing problems about chemical reactivity in the lanthanides. Well, why didn't Moseley get the Nobel Prize, and why has he slowly but surely slipped from the textbooks? Well, I suppose many of you know this, but it's a rather sad story. In 1914 and 1915, and in 1917, the Nobel Prizes were all awarded for X-ray work, the 1917 work being given for X-ray spectroscopy, which actually was pioneered by Moseley. There was no prize awarded in 1916, ostensibly because of the First World War, but the First World War also was going on in all of these years as well. Rutherford or both credited Moseley with having made atomic structure respectable, because towards the end of his life, Bohr recalled that in those years they were regarded as somewhat as crackpots, but history has shown that actually they were on the right track. And well, what happened to Moseley? Well, there's widespread speculation that Moseley would have won either the Nobel Prize in chemistry or physics, probably in 1916, had he not been killed. Moseley was a rather unfortunate victim of the Battle of Gallipoli on the 15th of August 1914. And the rather sad end of the tale of the British Association for the Advancement of Science is that Moseley fulfilled his obligations to the association. He gave a talk in Sydney, and it's said that he ran from the lecture room with a couple of his colleagues, caught a ship straight back to Britain, and then used his considerable social influence to be appointed in the Royal Engineers. He worked in the Royal Engineers, was sent to Gallipoli, and was shot while making a telephone call. So this actually leads to the other Moseley's law, which I think is probably worth mentioning. The British government, after that point, when there was a great outpouring amongst the scientific community about the waste of this, in the Second World War, people in Moseley's position, scientists, physicists, and people contributing to the scientific and technical knowledge of the nation were not allowed to join up. And I remember seeing Freeman Dyson give a talk once where he recounted what he did in the war and how grateful he was to Moseley. So part 2 of the talk is about atomic structure and inner shell spectroscopy. What were the consequences of all of this? Well, it's not the case, and I wouldn't want you to get the idea, it's not the case that Bohr or Moseley really worked out all the interpretations of Moseley's law on their own. And in fact, they had some correspondence, and nothing really quite worked out. They couldn't quite work out the factor of 3/4 or the z-1 factor, simply because Bohr was still in something of a confused state about precisely how many electrons were in the orbits. Bohr theory was a theory of one electron systems, but in the case of all of these elements, they have many, many electrons, and he wasn't entirely sure how many electrons were supposed to be here and how many electrons were supposed to be here. The resolution of this actually came from Walter Kossel in 1916 and 1917. Kossel proposed the octet rule in chemistry, but he also explained the factor of z-1 in Moseley's law in a way which still stands today. But he suggested that the factor of z-1 corresponds to shielding. If I have a point charge of z and I have an electron orbiting around, then if I'm some distance from that, Gauss's theorem of electrostatics says that I will see effectively a charge of z-1. And if that's the case, then the jumps must be between n equals 2 and n equals 1, and consequently everything fitted. The factor of 3/4 is 1 over 1 squared minus 1 over 2 squared, and the factor of z-1 comes from the shielding. Now, all of this was elaborated sometime later by Arnold Sommerfeld. Here's a picture of Sommerfeld standing in front of a chalkboard with his modification, actually, of the theory, where he replaced the circular orbits by ellipses and introduced the theory of relativity. He generalized Bohr theory, included relativity, and used it to explain the fine structure, which were the K alpha and K beta lines. Bohr was pretty excited. I do not think I've ever enjoyed the reading of anything more than I enjoyed the study of this particular paper. Albert Einstein was similarly effusive. Your investigations of the spectra belongs amongst my most beautiful experiences in physics. Only through it do Bohr's ideas become completely convincing. If I only knew what little bolts the Lord had used for it. The Bohr-Sommerfeld Theory actually contains a new quantum number, so there are now 2 quantum numbers, and the fine structure constant alpha, which has a value of roughly 1 over 137. And if one does a little maths for the ground state, you can expand out all of this and identify 3 terms. A term E equals mc squared, which is familiar to everyone. A second term, which is actually the energy of the Bohr orbit. And a third term, which you could call a relativistic effect. So the first term is just the rest mass energy of the electron. So the electron's always got that much energy. And then that energy is reduced by a certain amount due to Bohr theory. And then the relativistic corrections are the small deviations that Moseley observed in his X-ray spectrum. Later came quantum mechanics, and it's not my purpose here to discuss quantum mechanics. H psi equals E psi turned the orbits into orbitals and probability distribution functions. The energies E are exactly the same as those obtained by Bohr's theory for one electron systems. Dirac merged quantum mechanics and electrodynamics to explain the shortcomings of Bohr theory, which have been discussed already in the July lectures, particularly the interaction of electrons and radiation and an explanation of the mechanism by which energy is exchanged between levels, and very importantly, the Pauli exclusion principle for fermions and the Aufbau principle tells you what Bohr never really entirely worked out, which is how to put the electrons into the levels. This was extended almost simultaneously by Paul Dirac to include relativity in quantum mechanics, which actually revealed the origin of spin naturally as a consequence of the relativity principle and relativistic invariance. It was actually our friend Charles Dalton Darwin who solved the Dirac equation first for the hydrogen atom and showed that the energies of the Dirac equation for the hydrogen atom were identical to the Bohr-Sommerfeld model in every regard. And Dirac was asked, well, why didn't you do it? Why didn't, and he said, I was actually too anxious. Because in Dirac's famous papers on the Dirac equation, he actually solved the solution for the hydrogen atom in perturbation theory and showed that it was equivalent to an approximate solution due to Pauli. But he said, well, it just seemed that it might not work. And he said, well, you know how it is if you have a beautiful idea, you just can't necessarily go all the way, just in case you find something wrong with it. Charles Dalton Darwin had no such ambition. Now, the Dirac equation, this is going to be a bifurcation point of the talk. The Dirac equation for a free particle obviously has to satisfy the relativistic mass-energy relationship, E squared is C squared, P squared plus M squared C to the fourth. And the Dirac equation has to also have the same energies, and that's fine. And indeed, the Dirac equation does have those energies. But there's a problem, and that is that when you take the square root of E squared, you can get either a plus sign or a minus sign. The square root of 4 is equal to plus 2, or it's equal to minus 2. Now, in the case of the Dirac equation, classically one chooses the plus sign simply because stuff with negative energy doesn't make any sense, and particularly a particle that just has kinetic energy. And so there was never any trouble about this in classical relativistic mechanics, simply because there was no possibility of ever accessing any of these negative energy states. But in quantum mechanics, there is no basis on which to reject the minus sign. And in fact, on the basis of Moseley's interpretation of the X-ray spectra, all matter should decay radiatively from this plus solution down into the negative energy solutions, and anything you make out of electrons and stuff should be giving off radiation all the time. And this was a bit of a problem, which Dirac, in later life, was asked how he came up with the solution. He said, well, I knew a bit about Moseley's law, he said. All of these negative energy solutions, Dirac said, should be filled up with electrons. And if I were to remove one of the electrons from these negative energy states, it would behave exactly as if it were a positive particle. Now, he did have a bit of a false start on this, and he suggested that this positive particle was the proton, and there was some fairly unkind things said about it in the press about that. So he backtracked slightly, and he said, well, maybe this hole in the negative energy sea that I've filled up here, maybe this is a new particle unknown to science. And it wasn't unknown to science because in 1932 it was discovered by Anderson as the positron. And so here was an example of a theory, and we followed Bohr theory to Moseley's experiments, to the relativistic theory in classical mechanics, to the Dirac equation in quantum mechanics, and ultimately this explanation that all of these negative energy states are filled up to the Fermi level here, and that at the end you just subtract away the energy of the state, which is a form of renormalization, to actually give us the existence of a new particle and a solar laws. The neater explanation of all of this, we'll have to wait for 5 years of physics undergraduate course and another day. But the truth of it still remains. That Dirac had the insight which led to the development of quantum field theory, and that led us on the long and winding road that brought all of those particle physicists to our door last year to celebrate the discovery of the Higgs boson. So this was a bifurcation point in physics. It also led to Dirac's edict, which is the underlying physical laws necessary for mathematical theory are now completely known, particularly for chemistry. And that all of the work left is an explanation of the main features of complex atomic systems without too much computation. And this Dirac's edict actually underpins most of the work which is done in chemistry these days. And part 3 of this talk, I'll discuss X-ray scattering and the structures of materials, and ongoing work to determine the structures of biomolecules using intense X-ray sources. So the third revolution. Well, we're in the midst of revolution in science, in a world in which physics doesn't really stand alone in isolation of all of the other sciences, because physics has been at the forefront of developing new techniques and new insights into the physical world. And it's now widely felt that if physicists and the other disciplines would work together, we would actually be able to solve some of the grand challenges of science and questions of existence. And these the 3 revolutions are molecular and cell biology, genomics, and this concept of convergence, in which physicists and biologists work together for common good. Actually, in my world, there was a revolution 0, which occurred about 350 years ago, which was the publication of Micrographia by Robert Hooke, who's a sort of personal hero. Hooke developed some particularly powerful microscopes, and he was unusual in that when he was a child, he was trained as a draftsman. And so he was not only a fabulous scientist, but he was also extremely good at drawing. And so Hooke put together all of the drawings and all of the observations that he'd made through his microscope, and it became the first best-selling scientific coffee table book. So popular was it that it was reprinted 100 years later, but only with pictures, because the actual descriptions were rubbished by the Royal Society, partially because microscopy actually fell into disrepute in the 17th and 18th centuries, largely because of the extravagant claims made in this book, how microscopy would actually reveal the eye of God and the mechanisms of nature. And it actually started a craze of people going out and buying microscopes and telescopes to look up at the heavens and look at microscopic objects to divine the work of God. The pictures were exquisite, which is why it was the best-selling book of its day. This is the first use of the word cell in biology. It's actually the cross-section of a piece of cork, not the use of cell we have these days. And this is a fantastic picture of a flea, which was used by William Blake in his writings in the 18th century to dramatize the inner organism of mankind. But as I said, microscopy was regarded as the province of the gifted amateur for about 150 years. It was rubbished by people like Jonathan Swift. So Gulliver's Travels is actually an elaborate satire about microscopy and the pomposity of the Royal Society. And Blake's famous poem about to see the world in a grain of sand and heaven in a flower, to hold infinity in the palm of your hand and eternity in an hour, is actually to prick the bubble of the pomposity of microscopy. And Revolution 0 really took shape in 1959, as David touched on last week, with there's plenty of room at the bottom, where Feynman pointed out that the best way of answering fundamental questions in biology is to just look at the thing, and the best way of storing information is that there's no fundamental prohibition on the manipulation of matter or encoding information at the atomic level, and these have both led to advances in microscopy and advances in nanotechnology. Revolution 1, the most celebrated case of that was DNA. This is the celebrated photo 51 of the diffraction pattern of DNA, which was taken by Rosalind Franklin under circumstances which are very well known. And it contains information. The cross structure is characteristic of a helix or helices. The distances between these little black spots here tell you that the ladders repeat every 34 angstroms. The distance from here to here tells you that the distance between the rungs in the ladder are about 3.4 angstroms. And chemical information is used to restrict the allowable structures that you can put together that satisfy all of these constraints. And this is a thing, the idea of information and constraints that you get from diffraction, which we're going to come back to again in a moment. This led to the structure of DNA being proposed by Crick and Watson, and their model that they put together with old jam tins and bits of wire and Bunsen burner stands, which now stands in its own glass box in the middle of the British London Science Museum. The applications of this are to the development of pharmaceuticals, and in Melbourne the celebrated case is the development of Lenza, which was based on a knowledge of the crystal structure of the influenza virus. The H5N1 virus has the potential to decimate human population, and the drug that was developed from the knowledge of the structure of this molecule has the potential to save a very large number of lives should it actually enter the human population. Revolution 2 is the field of genomics. In the 1970s, supercomputers came along as the Quiney 1S, which I actually used as a student. So you know you're getting old when your first computer finds its way to the London Science Museum. When physicists were moving on to the second generation of supercomputers, biologists asked if they could use them, and they looked for applications. And this has led to computationally intensive uses such as gene sequencing and data mining and visualization applications, drug design and systems biology. So this work started off using the cast-off computers of physicists. These days, it's an operation in its own right. This is IBM Blue Gene Q, which has been installed in the Victorian Life Sciences Computational Initiative over in Grattan Street, VLSCI, and there's a very large room full of these very large boxes that look like something out of 2001. They're dark and menacing and they hum. This is set to revolutionize information technology in biology. Revolution 3 is convergence, large-scale interdisciplinary work applying the tools and expertise of fundamental physics to problems in the life sciences, where one utilizes large international research facilities, supercomputers, synchrotrons, free electron lasers, electron microscopes, and particle accelerators, whatever and whoever it takes to get the job done. So this is at least a part of the future of physics, collaborations outside our own discipline. So here's the evolution of microscopes. Here's Hooke's microscope. No one ever really managed to draw pictures with a microscope like this as well as Hooke, though it just works at art. This is a modern Leica super resolution confocal microscope from 2007, which ultimately can be regarded as the direct descendant of the Hooke microscope. It's optical, it uses lasers instead of just ordinary light sources. It uses cameras and detectors instead of just freehand sketching. But ultimately, this is the kind of the ultimate evolution of that technology. But what I'm really talking about here is using a facility which is 3.2 kilometers long, costs $2 billion to build, which produces femtosecond pulses of 10 to the 12 hard X-ray photons to actually serve as the light source for the microscope. So this is the end of the facility that makes electrons. The electrons zoom down this tunnel. There's a set of alternating magnets which causes the electrons to jigger as they go down. And in oscillating transversely as they go, they break up into bunches, which there's a spontaneous emission event which causes the bunches to lose their energy and to laze. The X-ray pulses shoot down this tunnel, and down here is the experimental hutches which perform the microscope experiments. Coherent light, I'll just touch on this briefly. The fundamental property of light that you have to understand is that light has an amplitude and a phase. And when you take a photograph, what you're actually measuring is the square of the intensity of the light. But this phase angle, which you imagine this vector going round and round, if I were to look at it side on, then I'd see the tip of this vector going back and forth as an oscillation of the electric field. All the information about this phase is lost in the act of measurement when I take a photograph. So coherent light sources, we have one in the neighbourhood. It's up in Clayton, though not for the reasons at Monash. It's actually in Clayton. It's the Australian synchrotron. This is a facility that's able to make variable light sources, infrared, X-ray, ultraviolet, and so on. And here is the X-ray free electron laser source, which produces extremely intense beams of light. So the question is, what is diffraction? If I have a beam of light and it hits a target, then the light scatters off the target and makes a diffraction pattern on the screen. So Steve, if you could...
Yeah. Turn the lights down and
let's try that.
projector off.
Projector... Hit what? B? So here we have, it's a pattern of dots, I believe. But the light is hitting the dots and actually diffracts out. So this is not a shadow image of dots. This is a series of point sources which are scattering, and I think you can probably see...
Turn the stage lights off.
Which one is room lights off?
Stage. Hit room.
Hit room.
And then there's stage.
Room. Lighting controls. Oh, yeah, stage. No, well, it doesn't matter. Don't want to waste time. You can see that there's a ring produced here. If you go to the next one. This is a different pattern, that's a different structure, and all of the information about the structure of those apertures is encoded in this pattern here. Can you find the one with the, that one? This is a regular pattern, so this is much more like crystallography, where we're shining the light on a regular series of holes, and each one of these dots actually is analogous to Bragg diffraction. So in X-rays we had a demonstration here where we had light being refracted off the surface and producing a series of spots. We could only see two with this apparatus. Here we have light impinging on a series of apertures, and each one of those acts as a point source, and each one of these bright spots actually corresponds to constructed interference between the light waves which are emanating. And this is an example of diffraction. How do I turn it back on? Spacebar. Excellent. Thanks, Steve. So this is our plan. If intense coherent light hitting things makes a diffraction pattern, the plan is to drop individual molecules into the path of the beam, collect the diffraction pattern, blow up the molecule, bring in an identical molecule and do it again. Each one of these molecules will drop with a random orientation, and if we collect enough data, we can assemble all of the diffraction into a three-dimensional volume, and then use that to reconstruct the molecular structure of the target molecules. So the name of the game is to collect diffraction data that looks like this, and then invert it to get the structures of the molecules. And if we could do this without making crystals, so without actually going to the trouble of going back to 1912 and invoking the spirit of Bragg, we could find the structures of molecules directly, which has the potential to revolutionize some aspects of biology. Now, the actual solution of this problem strongly resembles the solution of some well-known puzzles, in particular Sudoku. So when I go home on the train every evening, I see 10 or 15 people in the carriage all merrily solving Sudoku problems. Little do they know that they're actually solving problems which are known as constrained optimization problems, because you have a rule for mapping, a set of constraints, which is that all of the rows have to have the numbers 1 to 9. Set B is that all of the columns have to have numbers 1 to 9. And the mapping says that I'm allowed to put numbers anywhere, but each of the squares also has to have the numbers 1 to 9. And there's a great similarity between solving this problem and solving the molecular structure problem. Another example of this is the Enigma Code, where you have set A, which is the original message, whatever it is in German. Set B is the encoded message, which just looks like gobbledygook, and the mapping is the set of dials and switches and plugs in this device, which turns the plain language message into the encoded message. And the Germans, as many people here will know, believed that this was a foolproof encoding system, but it turned out that the weakness of this was human habit. There was one hapless chap on the north coast of France, and every morning he got up and had his orange juice, and then looked around and decided that nothing was happening, and he always sent the same message, nicht zu melden, nothing to report. And so they waited for him. They never shot at him, they never bombed him, they never went near him for the entire war, because he could be relied on always to send the message, nicht zu melden. So they got his message, and then they ran it through multiple copies of this machine until the first letter was N, and then the second letter was I, and once they got that, they were onto something. And then by about 10 o'clock in the morning, they found the settings of this box to decode the message, which they already knew was nicht zu melden. But once they knew his message, they knew everyone's message. And that, exactly the same idea, can be applied here for biology. Technically speaking, what we're trying to do is the solution of the mathematical inverse problem using a priori information and the method of iterative projections. If I actually spelled out what that is, the room would clear. So I'm going to invoke the spirit of Rutherford, who said, if you can't explain your physics to a barmaid, it's probably not very good. And I scoured the internet to find a picture of Rutherford where he looked like he'd been talking to a barmaid. But actually, it would be better if we could explain all this to high school students. And we do. As part of the program in CXS, we have an outreach program where we do explain how this decoding technology works. Here is the head of this initiative, Dr. Roya Barona-Nugent, who's a science teacher at Santa Maria College, Northcote, and she has developed a very elaborate outreach program which the students come to us, and they experience life in the School of Physics and the solution of physical problems. And you can do this at home. So Sudoku, some assembly required. If you make yourself 81 tiles out of foam board and the numbers 1 to 9 in 9 different colours of paper and the numbers 1 to 9 in white, then you can actually turn all of this into a board game. Of course we could write an iPhone out, but basically this is more in the spirit of Crick and Watson. Okay, Crick and Watson's machinery is all bits of wire and old jam tins and Bunsen burners, but it got the job done. You can get the same job done with bits of foam board and bits of coloured paper. And to illustrate how it works, imagine that these are 9 different coloured tiles. Each of them has the numbers 1 to 9, and on the reverse side of all of these tiles are white tiles. Okay, the white tiles are going to be the fixed tiles. And the only thing that I'm allowed to do, is to swap 2 tiles. Okay, the only legitimate move in this game is to swap 2 tiles of the same colour. I can't swap a blue with a, I guess it's an orange. I can't swap blue with orange, and I can't swap blue with salmon. I can only swap blue with blue, because in that way, I'll always have the numbers 1 to 9 here. And what I do is you go through and you make all of the rows have the numbers 1 to 9 in the first 3 rows, simply by swapping tiles of the same colour. And if you do that, a small number of swaps gets you there. Then you move down to the next set of 3 rows, and then the next set of rows satisfies the constraint. Don't worry about the columns, just concentrate on the rows. And finally you do the last set of rows, and you'll see that the numbers 1 to 9 appear once in each one of the rows. I haven't moved any of the white tiles, which are the fixed clues, and I always have the numbers 1 to 9 in each of these blocks. And then I go for the columns. So the next step is I make some swaps, and in this particular case, because time's running out, I fixed it so that I only have to swap horizontally, which actually doesn't change the status of the rows. So I can actually make all of these columns satisfy the constraint, which is, if you like, set B, simply by swapping horizontally the tiles. And then I can do it again, and I can do it again. So I can solve a complicated nonlinear optimization problem, which is the Sudoku problem, by a series of elementary steps in which satisfying the row constraint is set A, satisfying the column constraint is set B, and the mapping is actually the permutation operator. The only rule that I'm allowed to apply to any of the tiles is to swap tiles of the same colour. Now there's a precise analogy between that and diffraction theory. This is set A, which is the molecule, and from chemical grounds, I always know that the molecule can sit in a sphere of a certain radius, simply from its molecular weight. And set B is the set of diffraction data, and the mapping is actually the mathematical propagation of light between the molecule and the detector. And this is the second iteration of that scheme where I go to the detector, I satisfy the amplitude constraint, I go back to the molecule and I satisfy the support constraint about how big the molecule is. I've initialized this by just distributing electrons uniformly in the sphere. The first iteration of this was 0 everywhere. This was just a uniform charge distribution in the middle. And if I start the animation, why can't I see the cursor? I don't have a mouse. Touchpad. Yeah, it'd be one. Oh, that's going to. Here we go. So each one of these flashes is an iteration between the detector plane and the object plane. And you can see I started with no information at all, and within about 500 iterations, this is actually a reconstruction in 3 dimensions. This is the complete three-dimensional reconstruction of the molecule bacteria and Dobson from diffraction data, including the effects of damage and noise and statistical measurements and everything else. This is a problem involving a simultaneous solution of about 25 million unknowns in nonlinear equations, and one can solve it effectively exactly by the method of Sudoku, just scaled up enormously. The general idea is identical, and so this is how we explain how coherent diffractive imaging and how physics is going to make advances in biology by avoiding the mathematical complexities of the problem and finding suitable analogies. So current state of X-ray free electron laser science, 2 of the most distinguished exponents of this are Henry Chapman and John Spence. Henry Chapman was a student of Keith Newton, who many of you will know, and is currently the division director for free electron laser science in Hamburg. And John Spence did his PhD in 1973 and worked with Cowley, and is now the head of biological physics at Arizona State University. And a lot of the work in CXS was done, the CXS was the brainchild really, Professor Keith Nugent, who was the director of CXS from 2006 to 2012, but has now alas left us to the lofty position of Deputy Vice Chancellor Research at La Trobe. We're privileged to have Professor Leanne Tilley, who's a biochemist at Bio21, who is the current director of CXS. And the leadership of these two has actually placed CXS and the research that's been done in Melbourne and other places on the international stage in this emerging field of biophysics. This is sort of the logo at the center. So the summary of the talk is that Moseley was inspired by Bohr's theory to place the concept of atomic number on a firm basis. It stimulated research into the structure of the nucleus, into the atomic structure, into the Hartree-Fock theory, into molecular structure. It led the development of chemistry into the 1930s by people like Linus Pauling and Charles Coulson. It led to the realization that fine structure was a relativistic effect, to the development of the Dirac theory, and ultimately, as I pointed out, there was a bifurcation moment which actually led to what we now call particle physics and quantum field theory. X-ray scattering is the basis of crystallography and may, with the help of X-ray free electron lasers into the future, be used to study dynamical processes and actually take snapshots, molecular movies of biological processes as they take place. And future research in physics and biology will be linked through collaborative, interdisciplinary projects involving international facilities, much in the same way that particle physics operates, these free electron laser facilities. The papers that are coming out involve collaborations involving hundreds of people. So in this direction, it's not like laboratory science anymore. It's really like large facility science. And a parting thought from the man who inspired this year's July lecture series and the trilogy that we celebrate this year. Everything we call real is made from things that cannot really be regarded as real. If quantum mechanics hasn't profoundly shocked you, you haven't understood. Niels Bohr, 1885 to 1962. Thank you very much.
Thank you very much for that wonderful lecture. I think in view of the lateness of the hour, we might call for 2 quick questions before we close our proceedings. The young man, very enthusiastic.
You know about the positons and electrons? They like when we consider losing our electron, negative energy, and does it all lose their negative energy at the same time, or does it gradually lose it? If it's all at the same time, there won't be any accidentally moving into the same amount of positive and negative, or lose it at a time there will be a point in time where it has positive and negative. Is that the case?
It's a very complex question.
No, I think I can answer that. The picture that I showed you about the positron and electron obeys the same general ideas as the Bohr. So what happens is you start off with all the electrons filled up and there are no positrons. In order to actually make a positron, you have to have a photon come in. The photon has energy. The photon gives its energy to the electron, the negative energy electron, and pushes that electron up to be a positive energy electron. In order for that to happen, the amount of energy is enormous. It's a very hard X-ray photon. And the threshold for producing that is about 0.5 mega electron volt, almost 1 million electron volts of energy. But it's a discrete operation. It's either a positron or it's not a positron. And what you do is you produce a positron and electron in a pair. The hole which is left behind is the positron, and the electron which is produced is just an ordinary electron. And then at some later time, that electron or some other electron can drop back down in the hole, and photons will be given off. And so energy is always conserved, and it always happens in discrete jumps.
Thank you for that question. Maybe we'll take one final short question. I'll refer you also to the ABC website, which has got an essay we've contributed on the Bohr discovery. It was up for a brief time today before it was replaced with an article on Star Wars figurine. I think you can still find it. Okay, look, if there are no further questions, I'd like to thank you all again for coming. I would like to just remind everyone that we have one further lecture to go in the July lecture program for 2013, which will be given by Professor Rachel Webster next Friday, same time, same place, and I hope the weather will be better. And those of you who want more physics and want to hear more about the interaction between physics and biology, I'd like to invite you to come back here at 6:30 at an earlier time on the 2nd of August, where the inaugural Lady Visiting Fellow will be visiting us, Professor Kate McPhee from the University of Edinburgh, who has spent a career in working at the interface between physics and biology, and is going to build on many of the themes that Harry introduced here tonight. So thanks again for coming, and please welcome back next week. Thank you.